Correlation and causation. The learning outcomes include define correlation and causation in statistical settings, and critique studies for their use of correlation and/or causation statistics. Correlation is a test between two or more variables. It ranges from -1 to +1. The higher the absolute value of the correlation, the stronger the relationship. For instance, I am happy when I'm at the beach. The correlation between my happiness and a trip to the beach is likely to be highly positive. However, the trip to the beach may not necessarily cause my happiness. A less stressful environment, uninterrupted time with my family, time away from work, plenty of sleep, etc., may all cause me to be happy, while I happen to be at the beach. When I leave the beach, my happiness may go down, thus the two variables are negatively correlated when I leave. The relationship is statistically significant if the p-value is less than or equal to 0.05. In simple terms, you're highly confident that the relationship is not due to chance. Causation is much more powerful statement than correlation. Traditionally, business managers want to know which variables are causing sales to increase, new customers to buy more products, repeat customers to come on board, more students to enroll, more positive reviews to result, etc. Causation allows you to say that a change in one variable is not simply related to another, but causes another. Again, the relationships should be statistically significant with a p-value of less than or equal to 0.05. Here we see that ice cream sales and shark attacks are highly correlated. They tend to occur at the same time with each other. Neither causes the other, however. People buy more ice cream during the summer months when they're more likely to go to the beach, my happy place, and get in the ocean. With more people at the beach, it's more likely that someone will get bitten by a shark. Both shark bites and ice cream sales are likely caused by the summer season and increased people at the beach. We know from the previous slide that we need to use care when trying to make predictions based strictly on correlations. This scatter plot may make you cringe as you think back to basic statistics. Here you see a chart that shows sales versus advertising dollars. As advertising dollars have gone up, it appears that sales have increased as well. If we continue the scatter plot, we can predict future sales if we continue investing in advertising dollars, as long as increased advertising dollars actually causes increased sales. It's important to make sure that the two variables are causally related, not simply correlated. To start, the two variables must be associated with each other. That is, they must be correlated. When examining cause-effect, statistical significance of the relationship is more important than the strength of the correlation. The cause must happen before the effect. Whenever the cause happens, the effect must also occur. There are no alternative explanations for the effect. Non-spuriousness must rule out all other causes for what happened. The cause-effect relationship must similarly occur in other contexts. Let's look at our very simple example and see if the cause-effect criteria may be met. Given that the correlation between sales and advertising dollars is 0.634 with a p-value of 0.043, which is less than or equal to 0.05, the first cause-effect criterion is met. We measured the advertising dollars at the beginning of the year and the sales at the end of the year. So in this case, the cause happened before the effect. Every time we increased our advertising budget, there was a concomitant increase in sales. We have to think of potential alternative solutions for the effect. Was there a credit given for purchase of our kinds of vehicles? Maybe we offered new electric vehicles, which came with a large federal tax credit. Were there other advertising initiatives in addition to the one we managed that may have caused the increase in sales? While we created the advertising initiative, did our company design a new automobile that was very popular or fuel efficient, or fuel prices went down and we had the best minivan or SUV? Here it's difficult to rule out other causes, but we feel confident that none of these other situations occurred. Here we also have to make judgments, and it's important for us to understand the industry in which we are making statistical analyses. Have we seen similar advertising initiatives used by competitors with similar increases in sales? Have we used similar advertising initiatives with different product lines with similar outcomes? If all of these cause-effect criteria are met, then we may be able to initially establish causality. Other alternatives to causality include reverse cause fallacy. Instead of advertising causing sales, maybe we increase advertising every time we have increased sales. Maybe we were able to argue that we needed additional advertising because sales were increasing as a result of our previous advertising programs. Or perhaps we have a bidirectional cause fallacy. That is, advertising causes increased sales, and increased sales causes us to spend more on advertising. It's possible we have a common cause fallacy where there is another factor that causes both A and B. This is similar to the increase in shark bites and ice cream sales, which is of course a simplistic example. In our example, perhaps there's a push for more fuel-efficient cars due to high gas prices, and we happen to have the most fuel-efficient vehicle and it's in stock. The need for fuel-efficient cars causes us to, 1, advertise the fuel-efficient cars we have, and 2, sell more fuel-efficient cars. Maybe we are falling victim to the single cause fallacy. Maybe the 1 advertising dollars along with 2 new federal tax incentives, 3 in-stock availability of our fuel-efficient models, and 4 0% funding options all together cause an increase in sales. Sometimes what we interpret as causality, despite our best intentions, is simply coincidence or correlation. Finally, we may have selection bias. Perhaps we increased advertising dollars for our fuel-efficient models and had increased sales on those models. At the same time, however, customers stopped buying other models. Thus, we had a selection bias and only chose the cars or people that we were interested in. A bigger picture would have shown that overall sales remained the same while our advertising expenditures increased. It's hard to establish causality, while it's easier to establish correlation. In the real world, however, managers obviously want to see causal studies. While it's difficult to establish causality when conducting studies, particularly when you're asking people their opinions, there are some guidelines. Run experiments when you can control as much as possible about the environment. Use control groups and test groups, some who receive the treatment and some who do not. Think about drug trials as an example. We compared those who do and do not get the drug we are testing. Gather a representative sample of whatever group you're hoping to survey. Make and test hypotheses, with most of them made in advance or a priori. Conduct appropriate advanced statistics to help to determine causality if present. establishing significant relationships, correlations, are still valuable contributions to study. Now you know, just because one thing is related to another does not mean that one thing causes another. So if you take just one thing from this class, understand correlation does not mean one thing causes another. It just means the two are related to each other, which is still valuable to understand. We understand that correlation does not in any way imply causation. That's always been important when making theoretical assumptions, making hypotheses based on an understanding of the environment. However, Chris Anderson, Wired editor-in-chief, presents a provocative idea here. He suggests that we don't need the theoretical underpinning first. He says, who knows why people do what they do? The point is they do it, and we can track and measure it with unprecedented fidelity. With enough data, the numbers speak for themselves. This is an area where big data is leading the way, identifying patterns and trends in the absence of theories. Anderson goes on to say, correlation supersedes causation, and science can advance even without coherent models, unified theories, or really any mechanistic explanation at all. I appreciate these thoughts and give them some consideration. However, if you don't understand why people are, for instance, buying toilet paper off the racks, you may interpret increased purchases as a trend and get more toilet paper on your shelves long term. Obviously, there was an underlying cause for the surge in the purchase of toilet paper in 2020, and that's an extreme example. But Walmart will likely want to understand why data is suggesting they change purchasing habits prior to making big changes in their enterprise system planning models. Theory is not dead yet. In summary, correlation implies that two or more variables are related to each other. That is, they change in predictable ways in statistically significant manners. Correlation may be positive or negative, ranging from -1 to +1. Higher values imply stronger relationships, although p-values establish whether the correlations are statistically significant, typically with p-values of less than or equal to 0.05. Causation implies that one or more variables cause another variable to change in predictable ways in statistically significant manners. While causation is more powerful than correlation, both techniques are useful. Researchers should use multiple methods beyond statistics to argue for causality of variables. The ability to complete big data analysis quickly may change how we analyze data, but we should not forget theoretical rationale for relationships between variables. If we do, we may end up with a warehouse full of Charmin. Here are some of the references used in preparing this lecture.